All right, so this video is going to go over pages 8 and 9 in your work and energy packets. We're going to be talking about work. So number 1 says, what two different units can represent work? So remember we talked about joules being the main one. Okay, so that's just the letter J. Or if you don't want to do that, since I know we talked about impulse in the last unit and that had a J with it, you can also do a Newton meter. Okay, because remember, work equals force times distance. Force would be newtons, distance would be meters, so therefore it's a Newton meter. So either one of those two will work just fine. Now it says, number 2, in the following scenarios, determine whether work is being done or not. Okay, so what we're looking for is our force and our distance or displacement have to be in the same direction. Okay, so if they're not in the same direction, then no work is being done. Okay, so A is ice skater glides across the ice. Okay, so the ice skater is covering this distance. Now this one can be a little tricky. Okay, so what we're going to do is we're going to talk about is you have to apply a force to actually have work going on. Now if I said the ice skater was skating, actually like pushing off across the ice, that would be a force covered over that same distance. Okay, but in this case, this one is gliding, so technically a force isn't being applied. Okay, so this would be a no work scenario. And more, on the quiz and stuff, we'd probably be a little more specific. That can kind of go either way, so I wouldn't get too hung up on that one. B, skater's partner lifts her up a distance of 1 meter. Okay, so you have the skater being lifted up this distance, okay, going up, and the skater's partner is doing the force in that same direction. Okay, so therefore force and distance are in the same direction, so that means work is being done. Skater's partner carries her across the ice for 3 meters. Okay, so that skater's partner is using force to hold her up. Okay, but we're no longer lifting her, we're just kind of holding her in place. So that means as you're skating, her distance is going this way. Okay, so therefore force and distance are perpendicular, so this would be no work. Okay, so if force is perpendicular to your distance, okay, that is a no work scenario. Okay, if it's parallel, so if force is in the same direction as your distance, then that would be work. D, after setting her down, the skater's partner pulls her across the ice a distance of 10 meters. Okay, so you're pulling this way with a force, and that distance is going the same direction, so this would be a work scenario. E, after skating practice, the skater pushes her gym bag across the bench, so she's applying a force across the bench, and the bag is going that same direction, so this would be a work scenario. Okay, so a couple of instances where no work is being done is, one is if there's not a force being applied, then technically you can't be doing work. Okay, another scenario would be if force and distance are perpendicular, if one's going up and the other one's going horizontal. Okay, that wouldn't work as well. Okay, another one we didn't talk about in this one is circular motion. So if you had something where you are spinning it around, so let's say I'm spinning this around, your force is always going to be towards the center. Okay, and your distance or direction is always going to be tangent to the circle. So no matter how often you spin that thing around, your force is always going to be towards the center, and your distance is always going to be towards the outside. Okay, so that would be a no work scenario. Okay, so number 3, a woman lifts her 100 Newton child up 1.2 meters and carries her for a distance of 50 meters. How much work does she do? So I was given a force, I was given 2 distances, so let's take a look at what's going on. So I'm lifting the child up with a force of 100 newtons. Okay, so that's a weight. So remember, weight is a force. Okay, the distance going up is 1.2 meters. So they're both in the same direction. So therefore I can calculate work. So work equals force times distance. So we're going to do 100 times 1.2. And that's going to give me 120 joules. Okay, let's look at this distance now. So now she's holding the child. So her force is being applied this way. But she's carrying the child a distance of this way. Okay, so force and distance are not in the same direction. So that 50 meters doesn't matter. You're technically not doing work. Now, are you using energy? Yeah, but as for calculating mechanical work, we can't do it. So our answer would be just 120. 4, a 12 kilogram sack of grain is being hoisted up 5 meters to a shelf. How much work is being done? So I have mass, I have a distance, I'm looking for work. So work equals force times distance. Do I have distance? Yep. Do I have force? I do not. So remember, force is a weight. Okay, so weight is a force. So remember, weight is determined by gravity. Your weight would be different on the moon as far as Earth because gravity would be different. Your mass stays the same. So what you do is you take your mass times gravity to figure out what your weight is. So you're going to take 12 times 9.8. Okay, you can do negative 9.8. So in this case, since we're lifting it up, okay, so we're doing work in the up direction, we're going to make that 9.8 positive. If we drop that sack and now gravity's doing the work to pull it back down, then we could put it as negative. So in this case, we're just going to keep it positive. Okay, so 12 times 9.8. Let me actually calculate that real quick since I don't have that part. So 12 times 9.8 gives me 117.6 newtons. So that would be your weight. Now, do I have a force? Yep. Do I have a distance? Yep. So we can plug it into our force times distance. So 117.6 times 5. Okay, and that's going to give us 588 joules. A crane does 62,500 joules of work. So I gave you work. To lift a boulder distance of 25 meters. There we go. We're looking at a distance. How much did the boulder weigh? So remember, weight is a force. So that means we're looking for force. And what was the mass of the boulder? So we're also looking for mass. So I have work, I have distance, so I just got to solve for force. So 62,500 equals F times 25. Okay, so my force or my weight would be 2,500 newtons. So that's your first answer. Now, if you want to find mass, remember your weight is mass times gravity. So 2,500 equals mass times 9.8. Okay, mass is going to be, divide that, and you get 255.1 kilograms. So that would be the mass of the boulder. 6, a block initially moving at 3 meters per second, so that would be VI, is brought to a rest. So that's VF would be 0. Okay, by a 40 Newton force, so you're bringing it to a rest. So this is actually be a force of negative 40 newtons. Okay, so don't get too hung up on the positive and negative here. Okay, but technically, since it's bring it to a stop, it would be negative 40 in 4 seconds. So there's your time. How much work is done? So we're looking for work. So do I have a force? Yep. Do I have a distance? I do not. Okay, but if you notice, I have VI, VF, and time. Okay, that is enough to do my Daffy T. So time is 4, VI is 3, VF is 0. Distance is what you're looking for, therefore A does not matter. Okay, so you're going to use equation number 2. So D equals VI plus VF. So 3 plus 0. Doesn't matter. So 3 plus 0 over 2 times your time, which is 4. And that gives you a distance of 6 meters. So now I have my distance. I have a force, so now I can calculate work. So we're going to take that force, negative 40, times our distance, which is 6. And that's going to give you negative 240 joules of work. 7, a calf is roped by a cowboy and is pulled with a force of 125 newtons at an angle of 25 degrees above the horizontal. The cow is dragged 5 meters. How much work was being done? Okay, so here's your calf right here. Your cowboy is usually on a horse, so they're higher up. Okay, he's applying 125 Newton force. Okay, so there's your line right there. Okay, the calf is being dragged this way horizontally. We're not lifting the calf up off the ground. Okay, we're not slinging it up diagonally at the horse. It's just being dragged horizontally across the ground. Okay, so your distance is covering this way. You have an angle of 25 degrees. Okay, so I cannot just mix that 125 in with that distance because that 125 is not purely horizontal. Okay, I need to figure out how much of that 125 is horizontal by finding your force in the horizontal direction. Okay, if you notice, this looks like a triangle. Okay, so you have your hypotenuse, you have an angle. This side would be your adjacent. So we're going to use cosine. So remember, cosine of your angle equals adjacent over hypotenuse. Okay, so if you want to find fx, it would be your hypotenuse, which is 125, times cosine of 25. And again, make sure you're in degree mode, not radian. And that's going to give you a value of 113.29 newtons. So that's how much of that 125 is horizontal. Okay, so now we have the correct force. We have our distance, so now we can find our work. So work equals 113.29 times your distance of 5, and you get 566.45 joules. A broken down vehicle is being pushed at an angle of 55 degrees above the horizontal. Okay, so it doesn't matter, again, it doesn't matter how you draw your triangle as long as you just draw a triangle. Okay, so our angle is 55 degrees above the horizontal, so that's our angle right there. Okay, if 355 joules of work is being done over a distance of 25 meters, that means what I'm saying is your distance is going this way at 25 meters, and you're applying 355 joules of work in that same direction. What was the original force of the person pushing on the vehicle? That means, what was this force? What was my hypotenuse? So that means I need to figure out what was my Fx. Okay, I have my work, I have my distance, so I can find that. So 355 equals Fx times 25. Okay, again, we're just doing work equals force times distance. So that means your horizontal force in this case was 14.2 newtons. Okay, so that goes right here. Okay, so now you have your adjacent side. You have your angle. You're looking for your hypotenuse. So remember we said Fx equals your original force times cosine of your angle. So we're just going to plug in. So 14.2 equals F, we don't know, times cosine of 55. Okay, now you do not need to do inverse cosine or anything like that. You would simply do 14.2 divided by cosine of 55. So don't start putting 14.2 in that cosine. Okay, cosine of 55 is locked in. So just take 14.2 and divide it by cosine of 55. And you should get 24.76 newtons. So that would be your answer there. That would be your hypotenuse. 9, how much work is done on a 12 kilogram object when a force, so I have a mass, you're looking for work. When a force of 75 newtons is applied to it, okay, you have your force, to bring it up to a velocity of 15 meters per second, so that'd be your V final. In 3 seconds, there's your time. So we're looking for work. Do I have force? Yep. Do I have distance? I do not. Okay, so we're going to set Daffy T, see if we can get that distance. Okay, time would be 3. Your VF would be 15. You're looking for distance. I do not have A and I do not have VI, so I don't have enough to do Daffy T. So this is that longer problem. So remember, F equals ma. If I have a force and a mass, I can find acceleration. My force is 75. My mass is 12. Okay, and you're looking for A. So I'm going to divide both sides by 12. You get an acceleration of 6.25 meters per second squared. Now you know A, so you can just take that and plug it into your Daffy T. So 6.25 goes right there. That means we do not care about equation number 4. So we're going to use that one. That is D equals VFT minus 1/2 AT squared. Okay, so D we don't know. VF is going to be 15 times your time, which is 3, minus 1/2 A is 6.25. T is 3, and only T is squared. Okay, so what you do is you would solve for that, and you should get 16.88 meters. Now, there's your distance. We have our force. We have our distance now, so we can finally do our work equation. So work equals 75 times your distance, which is 16.88. And we're going to get 1,266 joules. Okay, so the key thing here is if you're looking for work, you have to have force and you have to have distance. If you don't have one of those, then you got to find it. Okay, so if you don't have distance, you're probably going to have to go back and do Daffy T. If you have enough to do Daffy T, great. Find your distance and then just bring it back to work. If you don't have enough to do Daffy T, that's probably a giveaway that you're going to have to find acceleration. So you have to do F equals ma. Okay, it all becomes very kind of repetitive. Okay, there's only so many ways we can ask it this way. Number 10, find the work done by gravity on the box. Okay, assume no friction. The angle of the ramp is 25 degrees, so our angle is 25 degrees. Okay, the length of my ramp is 1.5 meters, so my hypotenuse is 1.5 meters. Okay, so we're looking for work done by gravity. So remember, gravity is pulling this box straight down. Okay, gravity does not care about that ramp. Its goal is to simply get it from the top of the ramp to the bottom of the ramp. So again, that ramp could be 5 meters long, it doesn't matter, okay, or 1 meter long. Its goal is simply to get it from the top to the bottom. Okay, so if you want to find the work, which is work equals force times distance, okay, if your gravity is your force pulling down, your distance has to be the one going down as well. So that means, what is this distance right here? Okay, so we got to find the height of that ramp. Okay, so I do have a hypotenuse. I do have an angle. Okay, the x would be your opposite side. So the only function that uses that is sine. So sine of your angle equals opposite over hypotenuse. So that's what we're going to do. So sine of 25 equals opposite, which is x, over your hypotenuse, which is 1.5. So multiply both sides by 1.5, and you're going to get a height of 0.63 meters. Okay, so now we know how far gravity had to work. Okay, so we know our distance now. We just got to find our force. Well, I didn't give you a force, but I did give you a mass. And remember, you can find weight, which is a force, okay, because gravity is working on it. So my force would be mass times gravity. So my mass in my box is 2. Gravity is 9.8. And so since gravity is doing the work, we're going to make that negative. So you get negative 19.6 newtons. Okay, so that is your force. That's your weight. So now I have my distance. I have my weight or my force. So now I can do work. So work equals my force, which is negative 19.6. And since it's going down 0.63 meters, that's going to be negative 0.63 meters. Okay, so multiply those out, and you get 12.35 joules. Okay, so we wanted a positive work because gravity's doing the work. It's the one pulling it down. When you have a negative work, that means you're going against the motion. You're trying to stop it or slow it down. So in this case, gravity's doing the work to pull it down. Okay, if the value of friction is 8.5 newtons, what is the net work done on the box as it moves down the ramp? Okay, so now we're bringing in friction. Okay, so remember, the box is sliding this way. That means your friction is trying to stop you. So friction would be going that way. So that would be a value of negative 8.5 newtons, since it's trying to slow you down. Okay, now friction it has to work the distance of the ramp. Okay, so again, height doesn't matter at this point. Okay, friction is when the box is in contact with that surface. And that box is in contact with that surface all the way down the ramp. Okay, so I'm going to highlight this right here. All the way down that ramp. So that means its distance is 1.5 meters. So the work of friction would be negative 8.5. There's your force times your distance, which is 1.5. And you get negative 12.75 joules. So that's how much work friction is doing in this scenario. Now, net work means what is the total work being done. So you're going to add up all the works. So we're going to have the work of our gravity. So we'd add up all the work. So in this case, we would just you could plus a negative or just minus the 12.75. Okay, that means the net work would be negative 0.4 joules. Okay, so that is okay to have a negative work. Okay, that just means friction is doing more work in this case. 12, what are 3 scenarios where something is moving but work is not being done? Okay, so number 1 would be if your force is perpendicular to your distance. Okay, so if distance is going this way and your force is going this way, that would be a no work scenario. Okay, number 2 would be circular motion, which is kind of reinforcing number 1. Okay, circular motion is when your force is always towards the center and your distance is always going to be outside the circle. Okay, so that's going to make a 90-degree angle, which is perpendicular. So that would be no work as well. Okay, another situation would be where net work would equal out to 0. Okay, so that means that everything is balanced out. Okay, so if we're talking about free fall, okay, example would be falling at terminal velocity. So we kind of talked about that, is if you're like skydiving and you've reached your terminal velocity, that means the force of gravity is now being matched perfectly by the force of air. Okay, so there's work being done individually, but your net work would be 0. Okay, so those would be your 3 scenarios for that. So again, the key to this video is when you're trying to solve for work, you got to have force, you got to have distance. They have to be in the same direction. Okay, if they're not in the same direction, no work's being done. Okay, or if you need distance, you got to go find it. If you need force, you got to go find it. So you just need those two things. And that'll be it.